Hello, and welcome back to our last session for today. It's a great pleasure for me to have the guys from Too Fast Racing here on stage, and they will give us a presentation about successful Formula student combustion competition, participation. And yeah, we have here Thomas Geiger, Nico Trümper, and Dean Petrovsky. And yeah, I think they will tell you now how they managed to build the FSC winning car. So,
thank you. Yeah, just start right away and show you guys what you have to expect from us today. First, we will give you an insight of the Too Fast e.V., its history and team structure, followed by an explanation of the construction and conception of our MB-016 and the testing procedure we went through last season. Yeah, as you already said, me joining today, Thomas Geiger and Nico Trümper, both were the CDOs of the MB-016 past season and have been part of the Too Fast team for the past 2 years. They are both studying mechanical engineering at the Technical University of Munich. Yes. And my name is Dean Petrovsky. I'm part of the executive board of the Too Fast Racing team. I've been now part of the team for the past 3 years. And among others, I was the chassis leader in the 2015 team. Yeah, Too Fast team history. Too Fast was founded in 2002. After the foundation, it took 2 more years until the first competition-ready car was able to participate at FSUK. From then on, Too Fast developed every year a new car and started to participate not only at FSUK, but also at FSAE and FSG, only to mention some of them. In the season 2010 and 2011, we decided to develop our first electric car, the EB-011, and from then on we kept on designing each year 2 cars, a combustion and an electric car. Until 2013, the cars were almost equal. They had slightly chassis adjustments and a different powertrain. And in 2013, the cars were equipped with a full aero package, and which was improved and also adjusted to the new aero rules and as well to the concept decisions. In the past season, well, we achieved a thing I think every former team member who participated in a Formula student event, and especially at FSG, would have died for in our Too Fast team. We finally could accomplish winning Formula student combustion FSG. And I think we are very proud of it and thankful to be here today. But with this title, the limit is not reached, we think. So in order to keep the continuous development alive, we decided to join the FSG driverless competition next season. And with that, not only mechanical and electric engineers are joining our team, as well now IT, math, and all the robotics students are part of our team. And we are hoping to increase our know-how level by this. I skipped a date. In 2014, well, we decided to build 2 different chassis, 1 cylinders, 2 different concepts, a 1-cylinder engine for the combustion car and a 4-wheel drive for the electric car. And with this decision, new challenges had to be mastered by the team, and we could accomplish, well, as you see, the following successes. Starting with the statics disciplines, we have won the Combustion Design Award twice in 2014 and 2015. Finished last year 2nd place. And in the dynamic discipline, we could accomplish 2nd place in 2014, 2015. And last year, we won endurance and efficiency. So, yeah, enough history talk. Let me tell you something about the team structure. As you can see here, it's the last year's team with the cars. Too Fast e.V. is an independent organization supported by the Technical University of Munich and the sponsors. Currently, we have 200 members, but only 140 of them are active in the different sub-teams or subsections, which are the racing team and the eco team. The eco team is building a high-efficient electric prototype, joining the Eco Shell Marathon. Perhaps you know it. But today, more important, the racing team consists of the three sections: combustion car, electric car, and from this year on, the driverless section. And against the clear separation of the teams, the teams itself, they're working together and sharing know-how, not only because everybody's using the same office or workshop. The racing team structure is clearly divided in 4 stages. Here on this slide, you cannot see the first stage is the highest stage is the executive board, securing the budget and investments. And on the top of both racing sections, electric and combustion, the team manager is situated, followed by the CDOs of combustion and electric, and all the sub-teams where the team members are situated. So the racing team itself has, last season it had about 80 team members, and we are meeting once a week in a big team meeting. Every sub-team has once a week a meeting, and at TUFAS, you know, it's a big tradition to meet every 2 weeks for a meeting and to go on team drinking. So the team spirit is kept high, and the girls and boys get to know each other. Well, in 2015, we've created a slogan for our team. It's 1 team, 2 cars, 2 fast. We are building 2 different cars, but it's very important for us that everybody knows we are 1 team. As you can see at the, as you could see at the sub-team slide, we have a suspension. We have suspension teams and chassis team. They're building all together 2 different cars. We have a big alumni base. We are supported by them, and strong spirit. The team pushes every year to develop and build 2 different cars, and in order to participate in our most important competition, the Formula Student Germany. And in 2015, we created a short movie so that people can picture this team spirit. And I would like to finish my part of the presentation by showing you this clip. Mach leise.
So thank you a lot. Now you've seen our everyday life, and now I will go to a bit more in details and do a bit technical stuff. As Dean already mentioned, my name is Thomas Geiger, and I was responsible for the construction and the conception of the NBO 16. So what you can see here are the different phases of a season, and it always divides the season into 5 parts. So the starting is the conception of the car. It's followed by the construction, the assembly, the testing, and finally the events. So for the next few minutes, I'll give you a short overview as we as a team handled those different phases. At first, I'll talk about the workflow and the tools we use there. And afterwards, I will show you our decision for the overall vehicle as an example how to handle different concepts. So let's start with the conception. So what's the conception of a car? You can see on the right-hand side, the concept limits the car's performance. So every race car can only be as good as its concept. That's quite obvious. But furthermore, the concept phase provides the biggest possibilities to generate an advantage in performance, but it also has the biggest risks. So on the one hand, it's very easy and also cheap to get an advantage. On the other hand, misjudgments are nearly impossible to fix later on. We had one this season, and Nico will tell you some more about it later, so it's going to be interesting. All in all, the conception is a very iterative discipline, and every development starts with the conception and it defines your car. So how we try to handle this phase is mainly we have big 4 steps. The first step is a sensitivity identification. There we have a look at what parameters a race car and Formula student needs to be fast, or even better, to get the maximum potential in overall points. With this knowledge, you can ensure that you can make high qualitative concept meetings. So you will get a feeling for performance and can use this feeling in the concept meetings. After you pre-selected different concepts, you have to identify the properties of the concepts. So you have to make sure to get the numbers to evaluate the performance of all the different concepts, which would be the last phase, the performance identification. The soft facts and the point analysis you get out of this is the basis for a solid and rational decision. So, sensitivity identification. What's the main task? The main task is to identify the key parameters. So the question is, how many information do I need to know or to determine the performance of a car? Of course, there's a lot of difference between the FSC and the FSE car. And in my opinion, it's much more easier for a FSC car to get those parameters out of it. Afterwards, the parameters have to be evaluated on their sensitivity to lap time or to the total points. The methods we mainly use there is a self-developed 2-track steady-state lap time simulation, and there are a resulting competition point simulation. This will help you to develop a feeling for performance. In the concept meeting, it's mainly about creating the ideas. Afterwards, a short discussion helps to identify different perception and to reconsider criteria for exclusion. The methods there go from simple brainstorming to literature researches, for example about race car history or the evaluation of competitors. So, going to the property identification. There it's all about defining your concept. You have to create a deeper knowledge of your concept and of the soft facts. Soft facts are, for example, the packaging, the reliability, or the risks you take into account with the concept. The methods are there barely the normal engineering stuff like CAD, FEM, CFD, literature, datasheet, experiments. So after this phase, you should know all relevant performance parameters of the concepts. And finally, the performance identification. The performance identification is the evaluation of the performance of a concept. This is the basis for your concept decision. What we have is an overall point simulation where we can check if we benefit from the concept. So now let's get to our car. I'll show you how we came to our concept. So our car is mainly a lightweight aerodynamic car. It has not that much power, but it's very good in lateral G. You can see here the overall vehicle concept, the performance identification. You can see the different parameters that are enough to describe the performance of a car. Named, they are center of gravity, power, drag, grip, downforce, and mass. On the right hand, you can see the sensitivity of the lap time. So we make a variation of 10% of the parameter, and we have a look at how much the lap times change. It also should be mentioned that those sensitivities are highly nonlinear, so it's senseless to extrapolate widely for totally different concepts. The next step would be the concept meeting. In this case, you would just make different combinations of defining attributes of the race car. You can see here a high downforce car, a low downforce car, the amount of cylinders, and if you run a turbo or a compressor. So there are a lot of concepts. But from now, with your knowledge, from your parameter sensitivity, you can exclude some concepts from the beginning. For example, it's nearly impossible for a two-cylinder engine to gain an amount of power that can overcompensate the added mass compared to a single cylinder. And even more obviously, running a four-cylinder turbo engine not really helps. This helps to reduce the amount of concepts that are worth a deeper investigation to a minimum and saves a lot of time. So these are the resulting concepts. So you can see here you have now have to gain the information. You can see there's a four-cylinder aerodynamic car, a single cylinder with turbo, single cylinder turbo with aerodynamics, and a single cylinder with aerodynamics. So how do you gain the information? For the mass, it's quite easy. FSG provides the weight in the engineering design results, so no need to overthink that. Same with power and torque. Most teams publish the power of their engines, so you have very good overview. A bit harder is to define the stuff like downforce. We take the packaging therefore into account. So basically a single cylinder will provide you the most packaging space for your aerodynamic kit. So this results in a benefit in aerodynamics. Furthermore, regarding charged engine, an intercooler would decrease your potential for your downforce. So this is the result of the following simulation. You can see here the different concepts in the different disciplines. So let's focus on the single cylinder and the single cylinder turbo engine. The single cylinder high downforce is the yellow one, the turbo engine is the red one. And as you can see, only having a look at the dynamic disciplines like autocross, acceleration, and endurance, the turbo engine would outperform the single cylinder. So you would get some losses in skid pad because of the more weight your package will have and the increased center of gravity. But all in all, the turning point is the efficiency. So it's quite hard to build a single cylinder turbo engine that can keep up with the efficiency of a non-turbo concept. And those are the points that make in an overall scoring, as you can see on the right, the single cylinder concept the best concept in our opinion. And I think, as you can see in Hockenheim, we won the endurance and the efficiency. That's quite accurate description of the performance identification. So next step, construction. In Formula Student, the level of engineering construction at different teams is at a very high level. And even more important, it's very close together. It's very hard to gain a performance advantage out of the construction of a car. That's why I will try to focus on how we try to reach our conventional targets in the construction phase. So the construction really defines your theoretical performance. You can make a good concept rather heavy or rather light. So this will give the performance the concept on the track will have. As I already told, it's more like classic engineering stuff. You have predefined workflows and you just have to get stuff done. If you fail in this phase, it's hard and expensive, but most times it's you're later on able to fix it. In my opinion, the most important thing of this phase is a permanent target performance comparison. And there I will show you two tools we use there. So I think, or I hope every one of you knows this one. It's the weight table. I think it's one of the most important tables you have when building a race car. So for every assembly and sub-assembly, you will get a target. This will then define your total weight of your car and your mechanical balance. When starting with the CAD, everyone responsible for a part has to fill in their CAD weight once a week. So you always can track if you're in the right way, or if you're too heavy, or if the center of gravity is too high, or if the balance isn't okay. At the end, before mounting or before finishing any part, or before mounting it on the actual car, all parts are weighted, and this makes then the actual weight list. We tried very hard to reach our concepts and our goals, and we were about 1 kilo heavier than expected, and had the center of gravity very close to the goal, and also the mechanical balance was only 0.3% from our goal. So another thing, perhaps especially in our team, is the aerodynamic table. So this is basically an overview that helps you to track the aerodynamic development. It's mainly automatized out from the CFD simulations, and you can always have a quick overview. One important point there is the estimated weight, because there's always a trade-off between the weight of an aerodynamic part and the downforce it creates or the drag it reduces. So for every change you have to estimate the weight, and then you can use your sensitivities to have a look if it's worth mounting the part or not. So then I will go on with Nico. He will make his part.
All right. Thank you. Now we will go on to a chapter which mostly decides about a successful Formula Student season. It's about testing. Our goals for this season were set by reflecting the last 2 seasons where we had a really great performing car, but it was just not reliable. In fact, I still remember this sentence, which truly came from another team member who was passing our box in FSG 2015, and he told his teammate about us: Too Fast always builds a really fast car, but don't worry, they're just not reliable. So we also thought about this. So back to our goals, which were this year at least 6 weeks of testing before set of race camp. 2 weeks from that, we wanted to test without aerodynamic devices for 2 simple reasons. The first reason, we wanted to get rid, how we say, of the childhood diseases. As far as I know, every team has these diseases or these problems, and they are not very difficult to solve, but they just cost you valuable testing time. The second reason, we are more focused on getting all things like sensors, wiring, and more properly running before we can focus on the performance of the car. After this time, 4 weeks of testing with the completely car was the focus. By the way, to split up testing in these 2 chapters just gives the aerodynamic sub-team more time to build their parts in perfection, which means having very tiny gaps between the flaps and the end plates, and having an even and smooth surface finish. After we came back from testing, they also had time to align their parts as close as possible to the virtual construction. And indeed, this takes a lot of time. But we said if we spend so much time on CFD simulation and our undertray is in reality 5 or more degrees wrongly aligned, then it's not worth to make simulations this extensive. Back to the 4 weeks of testing, where we do performance analysis and try to find a proper suspension setup by changing stabilizers, track angles, ride height, damping setup, camber angle, and more. Let's go to the procedure of our testing days. On the day before, we set up a test sheet with a timeline where every sub-team has its time slots to test things. We also have a very strict rule of doing our checklists on the car. So unless the sub-team's engine, suspension, chassis, and aerodynamics haven't checked every screw on the car, there will be no testing the next day. There's always the same persons doing the checklists, and they get a sheet where they have to sign afterwards. Once we are on the test track, we try to keep up with the timeline. We want to get as much data as needed from our car, so the responsible team members can analyze while different team members do quick setup changes on the car. Splitting up this work gives us the possibility of doing back-to-back testing without having too much influences of the surroundings, like track temperature and tire temperature changes. For us, this is very important in case to have comparable data with the same circumstances. Like I already told you, data logging is very important for us, helping to analyze the behavior of our car. Therefore, we have lots of sensors mounted, such as damper putties, brake pressure sensor, tire temperature sensor, gyro, wheel speed, airspeed and pressure, steering angle, our rear axle steering position, our DRS position, shift, clutch and oil pressure, oil and water temperature, and even more. The software we are using for analysis is from Motec called E2 Pro. For every testing session, we are doing documentation. Our main purpose of this is to inform everybody of the team what was happening at the testing day. In this documentation, we will give for each sub-team a quick overview what problems occurred, especially on which part, so they know what they have to fix. Also, we are selecting a list of the top 3 performance problems and the top 3 technical problems. So everybody is aware why we are losing testing and lap time. Now we will get to a topic which cost us multiple sleepless nights. And at this point of the season, we also thought we are not going to any competition at all. As we all know, and of course some other teams have already experienced, monocoque failure is the last thing you want to happen during the season. So just 10 days after we did the first ride, we tested our car still without aerodynamic, and an accident happened. Our muffler end cap fell off and got separated from the middle CFRP part while driving, and it got under the rear left tire. The suspension compressed too much and caused the bell crank attachment point on the monocoque to fail. This happened 4 days before rollout, so we got help from a company by locating the damaged parts of the honeycomb and the delaminated layers via ultrasonic scan. After our rollout, we took the NV to the workshop and disassembled it in the same night to the bare mono. We finished in the morning, and luckily after more than a week, the NV016 was back on track. But only 2 weeks later, the next big thing happened. Our new film adhesive, which connects the outer layers to the honeycomb, didn't do its job like it should. At the beginning of the season, we decided to take a much lighter film adhesive than the last year, and of course we did experimental tests to compare these 2 adhesives. And it also turned out that the new one was much better than the one we used. So now, as you can see on the middle picture, there are white spots marked around the suspension, and they were all delaminated from the honeycomb. So this means these points were moving. It's not good to drive like this. So this turned out to be the biggest nightmare as we located more and more spots on our monocoque. Luckily, this also happens sometimes to professional motorsport teams, and we also found a solution for this to fix. But again, disassembling the whole car and repairing cost us again more than a week. Just in time, we made it to ZF Race Camp to show the performance of our car. And as you can see on the picture with our pads on the head, which is a too fast habit, everybody was happy to see the car running again. I also took this kind of picture to remind everybody who is participating in Formula Student that even though the competitions get more and more serious from year to year, that there always have to be fun moments in the teams. Formula Student teams are still non-professional motorsport teams. Back to the ZF Race Camp, which is the very first big test for our car. By then, all scrutineering problems have to be fixed, and no more major changes on the car are allowed. Lessons we learned from the testing is that even 6 weeks of testing can sometimes not be enough if a bigger problem like monocoque failure happens. Now, another thing we learned is that experimental static test of the new film adhesive was not reflecting the load changes and vibration from a single cylinder engine, which occur in reality. And even if nobody on the team thinks this kind of failure is repairable, then seek help to experienced companies and you come to the conclusion that everything is repairable. Now a few key facts of the car. The NB has a rear axle steering which is controlled by velocity, driver input and steering angle. On the rear axle we are running a single inboard brake with a spool differential, and in consequence of that we are able to have a completely closed one-piece CFRP rim. The engine is a KTM 570 single cylinder. This setup combines the biggest displacement with the lightest and smallest bell crank housing of a 450 engine. A drag reduction system is also installed. Hereby we get to a total weight of, like Thomas said, 160 kilograms, 45 kilowatts of power, 56 Newton meters of torque, a CLA of 6.0 and an overall efficiency of 3.2. Now we get to the last two slides of our presentation. Why were we not successful the past years? Thereby I mean in overall placement. It becomes clearer if you look at our competition results from the past 3 years. Since 2014 season, we did not finish 8 out of 12 endurance. But in the same time, we placed 8 out of 12 autocross in the top 3. And we won 484 points out of 450 points in the last 3 years of FSG engineering design. So, this means new concepts mean less testing time, and new innovations bring more risks to fail with it. So there's a target conflict between innovations and reliability. Maybe this year we got the right amount on both of them to win FSG combustion. Nevertheless, for us, this is what Formula Student is about. Showing courage and creating new concepts every year. And even if the concepts fail, you will learn from that. Thank you for listening to our presentation. We will all see you at FSG 2017. And if you now have questions, you can ask them.
Yeah, thank you very much for that. Do we have questions? I think you said it all. You said how you have to do it. No, you know, and that's it? I don't think so. I have a question. Actually, several questions. Let's start with the first part. Your new team members, how do you recruit them? When do you start with that? What do you ask from them, time-wise, for example?
Okay, so I try to answer that. Basically, too fast always starts too late. So we know many of you guys really start before the ending of the previous season. We are not able to do that. We have to go with 2 cars through the season, and we don't have enough amount on guys, on girls and manpower to do recruiting while this happens. So basically, after the last competition, the new team leaders take like 1 or 2 days off, and then they start recruiting. And recruiting is, we have different Stellenanzeigen on Facebook, and we also make some information evenings where all the guys can come and can inform themselves about Too Fast. And we go to the lectures and we try to reach people and to tell them how great the concept of Formula Student is. So I hope this answers the question.
Okay, so you tell everyone how great this is, and do you take everyone who wants to join your team, or do you say, okay, if you want to join us, we expect you to be there at least, I don't know, 2 days a week, or 20 hours a week, or 5, or do you have something like that?
Okay, so we don't have a specified amount of time every team member has to be in the week. And also, because our student schedule is very tight, we cannot expect that they do not write any exams or only concentrate on the Formula student. So I think it's a trade-off like always. If you invest more hours, you will learn a lot more. And most of the times the guys start with, I think, 5 to 10 hours, and then they really getting into it. And later on, you won't have to ask them because they come like 50 hours a week. So, but it's not really strict rule for how many hours they have to spend.
Okay. Thank you. So, we have other questions.
So you're using a lot of methodology. I think that's impressive, but I don't think you developed it in 1 year. So how do you gain the ideas for those processes and, for example, for the comparison between points and performance and so on?
Okay. So the tools are long-time developments. So, for example, the overall point simulation started in 2012 and was mainly finished in 2015, so that so it's easy enough for everyone to use it in the team. And yeah, mainly they are from guys that are not really involved in the actual season, so they can concentrate on their tool. And from the workflow, I think it's what you need. So you go through a season and you think, oh, it would have been great if I could make this decision with this information. And then, okay, for next year we need a guy to develop this tool, and then we try to get it done.
So do you have single guys who are just focusing on those methodology, or is it, I mean, in kind of leisure that you think about these tools and maybe you have some research about it?
Yeah, there's one guy that is responsible for a tool and develops it. So if it's really the tools that are self-made, for example, the point simulation is MATLAB-based. So there's one guy in the season that is responsible to make the code better and to make it more accurate and to provide the tool for the other guys that they can use it. I hope this was the question.
Yeah, I meant things like the table, for example, that you are using those kind of tables, for example, for the weight or so on. That you have, for example, some kind of scripts that all team members can just fill in.
Yeah, the CFD table is basically a small Java applet that makes the results from the simulation directly in the table, so you don't have to do it manually. And the weight table, they have to do it manually. And then it's tracked by the team leaders. And if you don't do it, then you have to pay beer.
Okay, thank you. We have another question here in the back.
I have another question that maybe extends on the simulation that you mentioned. If you use this tool for multiple years in a row, how do you generate new concepts? I mean, if you would have to change your assumption or things like that if you want to come to a different optimum point. So how does that work?
Okay, that's quite an easy answer. So talking about the rules, every time there are new rules and then there's another optimum. So maybe with the rule change, for example, from 14 to 15, with the big restriction in aerodynamics, it was more important to get more aerodynamics because the ratio from the aero load to the mechanical mass of the car decreased. And so you have to put your spotlight more on the aerodynamics than before. So there would be a new optimum. Also, you have to analyze your competitors because when there's a car that is very fast, like, for example, GFR was several years very, very fast. You know, you really can't beat them in endurance. So then you have to save more fuel, for example, to be better in efficiency. So you always have to look at the other guys, what they are doing. Same with 4-cylinder cars and acceleration versus single cylinder.
Okay, thank you.
Thank you. There are more questions. There is one more on the other side of the room.
Thank you. How do you guys introduce new team members to software, like CFD or?
Basically, that's kind of the job of the alumni, so they take their time and they work together in the beginning. So there's a phase where hopefully the most alumni come in the evening in the office, even if they are not in the team anymore, and then they try to work together and they explain their stuff. And there's also like a wiki where the information is stored, but mainly it's really with personal contact, because it's less, you have a less amount of time to get the information to the new guys, and for the new guys it's always easier if they have a direct person to talk with, and so they can learn faster and ask questions. And nowadays it can also be done via remote desktop or stuff like that.
All right, thank you.
Yeah, thank you. Are there more questions? Regarding your tool, what you use to find out your sensitivities, you said that it's a self-developed tool for the simulation, and also you said that the sensitivities are for sure non-linear, so you cannot take them for granted. How accurate would you say are you in the simulation when you come to a completely new concept? I mean, if you know your car for sure and you know all the parameters, it's okay, but if you have to go into something very new?
Yeah, of course, somehow it differs, but if you have the old car and you do your sensitivity analysis, you can change things. So easy thing is changing the power. So if you go to the test track, you make one lap, then you change your lambda value, then you make the next lap, and then you can have a look at your data and know how much power you lost with the new lambda. You can do the same with your simulations, and so you can spread your sensitivities over a wide variety of parameters.
Okay.
Same with mass, downforce, stuff like that.
So you actually try to do it on the test track as well, the sensitivity analysis that you did before in the simulation.
Yeah, of course, if you use such powerful tools like overall point simulation, you have to make sure they are true. So mainly if you base every decision on this tool, it should better work out. So you have to put a lot of work in validation of these tools. For example, also gaining tire data or validate your sensitivities.
Yeah, clear. Very good. Are there other questions? Use the chance now. No, I think not. Okay, then again, thank you very much for being here.